Get some properties down about chords. So 10.3, fill in the blanks, please. It says, in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So in the circle that's provided for you, put a center point. Then make a chord AB. You think, Clementi, put your phone away, please. Then make a chord BC. So then make your radius from center to A, center to B, center to C. So what theorem 10.3 tells us is if these chords are going to be congruent, then the arcs created by those chords will also be congruent. Okay, everybody identify where those chords or those arcs are. So AB has endpoints at A and B, so it creates this arc, which I highlighted there in purple. BC has endpoints B and C, so it creates that arc. So if my chords are congruent, then it is true then that the arcs created from them, so arc AB will be congruent to arc BC, is what this theorem is telling us. Okay, so the moral of today's story is going to be you're going to have a lot of equal things. So just start equaling everything together. You should be to a good bet. All right, so if we look at the first example, do we have congruent chords? Yes, so if we have congruent chords, then that means that the arcs created from those chords will also be congruent. So if the one is 108, then the other one's 108. So the measure of arc CD is equal to 108 degrees. Easy enough? Yeah? Dylan, we're focusing here, please. Theorem 10.4. If one chord is a perpendicular bisector, perpendicular means 90 degrees, bisecting means what? Good. Making into two congruent parts. So if one chord is a perpendicular bisector of another chord, then the first chord is going to be a diameter. So in your diagram, make chord SQ. Go through as much to the center as you can to make it look like it's a diameter. Then put chord TR so that it looks like it's perpendicular to SQ. Their intersection is occurring at point P. Put in your right angle, put in your congruent marks. Can I please not throw things? So, if you are given a perpendicular bisector between two chords, then it's true that the length that is the perpendicular bisector, in this case is SQ, is going to be a diameter, meaning that it will go through the center of the circle. So now we can do the converse of that in theorem 10.5. So if I know that this is a diameter, then I know that the chord is going to have to be a perpendicular bisector. So in theorem 10.5, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord, but it's also going to bisect the arc. So, in your circle, put diameter EG going through the center. That's why I know it will be a diameter, because it's going through the center. Then make a chord FD look like it's perpendicular to the diameter, intersecting at point H. So what this theorem gives us is we have a diameter perpendicular to a chord. So that means that the diameter is going to bisect. So it's going to bisect the chord, which means that we get FH is congruent to DH. But what we also then get is that this minor arc will also then be bisected. So this will be congruent to this. So those two arcs will be congruent. So arc DG will be congruent to arc FG. So if you're given a diameter that's perpendicular to a chord, then you get these two congruencies. Okay. All right, so if we look at this example, do I have a diameter, yes or no? Yes, AG goes through the center of the circle, intersecting at point F. It's perpendicular to the chord DB, so since it's perpendicular to, that means that it bisects it. So if this is 10, that's 10, so what's the length of BD going to be? Yeah, BD would be equal to 20. Now I'm going to add to this, just for fun. Let's say that arc AD is 60 degrees. What would be arc AB? It would also be 60 degrees. Good. How could you then get the rest of the circle's degrees? So we've got two options. From A to G should be how many degrees? 180, because it's half a circle, right? That's a diameter. So if this is 60, then from D to G should be 120. And then B to G should be 120. Another way we could have gotten there is we could have done 60 plus 60, which is 120. Subtract that from 360, which is 240. So that means from DGB should be 240. If these are the same, then these should be the same, and then we cut that in half and get us back to the 120. Right? So either way would get you there. All right, flip on to the back. Moving on. Let's see if we've got this. So, BD, how do I know it's a diameter? Goes through the center. It is perpendicular to the chord CE. So since it's perpendicular to, it bisects it. So this is congruent to this. But that's not going to help me out because I don't have anything here. But then I know that the arcs are also going to be congruent. So before I can get any of my actual degrees, I need to solve for x. And to solve for x, the moral of the story today is just equal everything together. So 9x equals 80 minus x. Add x to both sides. So 9x plus 1x gets us to 10x equals 80. So x is equal to 8. Okay. So C to D is 9x, but we just said now that 8 is x. Yeah, so 9 times 8 gets us 72 degrees. So arc CD would be equal to 72 degrees. Yep, so DE would also then be 72 degrees. So now we got to find C2E, right, shortest distance. So 72 plus 72, so 72 plus 72, or 72 times 2, which is 144 degrees. Okay. How could you find CB if you were asked to find CB? Well, from D to B would be 180. Yep, so 180 minus 72 is what, 108? So this would have to be 108, which means this would also have to be 108. Okay. All right, very good. All right, next theorem, 10.6, tells us that in the same circle or in congruent circles, two chords are congruent if and only if they are fancy word for equal distance, equidistant. Equidistant from the center. All right, so in our diagram, we got a lot going on in this one. We've got center E and circle E. And you've got chord AB. And you've got chord CD. So those are my two chords. Then I've got these tiny little lines occurring from the center to those chords. Well, those are representing the distance that they are away from the center. And it's perpendicular because your distance needs to be perpendicular from something. So if your distance, so FG and FE are the same distance away, then your arcs or your chords are going to be congruent. So that's what this says down here. So AB is congruent to CD if and only if the length of EF is equal to the length of EG. Again, got a lot of equals, a lot of congruencies. So we're probably going to be setting things equal to each other. Okay, so these need to be the same. They're the same length, then I know that the chords are going to be the same. So if the chord is the same distance away from the center as the other chord, then the chords will be the same. Okay, let me give you a visual here for a second. So here I have a chord that's, let's say, is 3 inches away. And then here I have a chord, let's say, that is 3 inches away. They're the same distance, then they're going to be the same length. If I make this chord go to, let's say, 6 inches away, did that chord become larger or smaller? Not larger. Why is it smaller? Why did this just get smaller from here to here? It's further from the center, and plus your arc created is getting smaller, right? Okay, so if they're the same distance, then they're going to be the same length. If I were to make it go to just 1 inch away, then it would definitely be larger than all those other ones because the arc created by it is larger. All right, so last example. Are my chords congruent? Yes, so if my chords are congruent, what's true about the distance away from the center? They're going to be the same, so let's first solve for x. 2x equals 5x minus 9. Subtract your 5x from both sides, which gets me to negative 3x equals negative 9. Divide by 3 gets you x is equal to 3. So what's the length of CU going to be? Okay. So CU is equal to 2x, which is 2 times 3, which is 6. Done and done.